See. So today's video, I just want to attempt to explain research that I got to participate in during the fall of 2024. So this is titled Gravitational Orbits and Dark Matter Arising from String Theory. Now, I am not a string theorist myself. In fact, I have just dropped out of college recently. So I don't even have a bachelor's. Okay. But what I understand is that string theory has given us a lot of mathematical tools which we can use in other fields of physics, specifically right now in theoretical quantum gravity. Um, 99.9% of this research was done by Professor Vincent Rogers, our advisor. Um, the other 0.1% was simply uh, myself and my colleague Eddie. It was our responsibility to uh, organize this poster for a conference, a research conference, and then to present it to the best of our knowledge and to do our best to do it justice. Now, this was again in the fall of 2024, so it's been a hot minute. Um, I've spent some time before this recording trying to brush up on what some of this means. We'll see how well I do. At the end of the day, this video is just meant to kind of showcase the research opportunities you can have during your undergrad years, at least in American institutions, um, as a theoretical quantum gravity physicist, and just sort of showcase also some of the things that I've been exposed to. So let's get started. Let's see if I can. Yes, perfect. Um, okay, so this little chunk here is a sort of background piece. So Einstein, we have to thank for special relativity, as well as some other physicists, but general relativity is the big player here, which was developed 10 years later, um, or over the course of 10 years, I should say. General relativity is very rigorous mathematically. As you can see here, we're talking about space-time being modeled as a four-dimensional curved manifold described by a metric tensor. So you have tensor calculus, you have differential geometry. Um, Sometimes you'll see algebraic topology. I mean, it gets very advanced, mathematically speaking. Um, with that said, action. So I don't fully understand action. I've read a bit of Feynman's lectures about it. But I do understand that particles in space um, follow the principle of least action. And action is given by S is equal to the integral of the Lagrangian with respect to proper time, I believe. Um, in this project, I believe we've done something other than we parameterize proper time to a different range or something like that. That's why lambda is used here. Um, where was I at? Oh, yes. And so it's the change in that action, S, so ds, delta S, whatever, um, that we want to minimize, because particles follow uh, whatever path in space-time, geodesic, we call it, um, that produces the least action. So if you solve this, ds, blah, 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 Lagrangian will give us equations of motion, and it is those equations of motion that will describe the particle following the principle of least action. Okay, so here's the Euler-Lagrange equation to find the path that minimizes the action. Um, do some substitutions and using Christoffel symbols, which you can see this 1/2 inverse metric tensor, and these are partial derivatives of metric tensors with specific uh, down indices. We get this equation. Now, as you may have noticed, and if you didn't, that's all right because it took me forever to understand this, and even now I'm questioning if I understand it. But this is acceleration. This is the space-time curvature, right? And these are velocities. So if we were to flip this around, we would have acceleration, right, is equal to negative velocity squared. Um, if you think of the wave equation, that feels pretty similar, right? Uh, Not a coincidence. Anyways, if we solve this equation, it's a differential equation, as you can see. If we solve this equation for um, x of u, blah blah blah, we'll get our equations of motion, which minimize the action. And this is again the space-time, um, not constant. This just tells us what the space-time is happening. So actually, in this project, we look at cases where space-time is flat, meaning this is zero, and we end up just having this, like acceleration is equal to zero, and we're solving second order differential equation. Okay. Um, okay, so this part is very advanced mathematically using equivalence classes, um, n-dimensional and manifold projectively invariant. Doesn't change as we rescale or reparameterize the object in an additional dimension. I don't understand this mathematics. This is, yeah. Um, but again, we get, when we consider the associated geodesics, and we get the following equations of motion. Here, we can find, oh, these are where we get our following equations of motions from. Um, yeah. And from string theory, we're interested in the diffeomorphism field. Um, Again, it's really painful. I think at some point I understood this well enough to talk about it, but I don't follow. So um, these are some examples of geodesics. So a particle on this manifold would travel that way. And each of these lines on this weird bat dog thing would follow this line, the line that minimizes path that minimizes action. Um, Deeper into place two. Two is this. So this is our equation, um, the geodesic equation. Thank you, Past Landon. The geodesic equation using this lambda and the diffeomorphism field that arise from string theory. So diving deeper into that equation, we're interested in understanding how these two affect the equations of motions as they vary. We can better understand this relationship using, right, the Sturm-Liouville equation to solve for lambda. So um, acceleration of lambda with respect to tau plus lambda times the uh, diffeomorphism field is equal to zero. We solve this equation and it gives us solutions of lambda. As you can see, we factored these up. Now that lambda can be found, uh, right, we find a force of interest. Now this force is with respect to, we're going to call it the Thomas Whitehead force, because this is all related to the Thomas Whitehead theory of gravity. I shouldn't say theory of gravity. Thomas Whitehead gravity. I'm blanking on the word. It's a framework. Framework for gravity. It's not exactly a theory yet. I think it's. I mean, it's been the life's work of Professor Vincent Rudder. So, um, anyways, we get this force. When this force is zero, Thomas Whitehead theory collapses to standard general relativity. Our diffeomorphism field is zero when this is equal to zero. We do a bunch of parameterizations. I really didn't understand this part. This is intense, rigorous mathematics that Dr. Rogers worked on. Um, we also map our proper time into negative one half and one half. So the entire universe is working on that time frame. Um, but we get this, and we set this equal to 0. We solve for yeah, something. If anything, this video should showcase that doing research is always learning, because you're always learning something, because you never know everything. And if you enjoy that thrill of not knowing something, I highly recommend doing research. Um, I mean, that's why I do it. That's why I'm still making this video, even though I don't know what I'm talking about, because um, I'm not like humiliated. I'm actually excited by the fact that there's a whole rich world here that I don't understand. So, second order differential equation right here. Um, and we, when we solve that, we're going to get A1 and A2, I believe, are velocities, initial velocities, yeah. And then C1 and C2 are like, yeah, they produce different families of solutions. And then integer n stands for energy of some kind of the diffeomorphism field. Um, so these are just random, arbitrary values of C1, C2. But as you can see, the force is a little weird. So the force, which is proportional by mass to acceleration, you can also think of that F equals ma, right? Acceleration is negative. It's like, in fact, we'll look at things as the jerk. The jerk is linear, and um, that happens in everyday life. Um, yeah. Um, well, I shouldn't say that, but and then here the jerk is like almost uh, not quadratic, not quartic. The third one, the one in between, uh, cubic. There we go. Um, yeah. Here's the big kahuna. This is the part that I well understand. So this is the position with respect to proper time. Okay. A free particle is just linear, right? Um, whereas a particle in this diffeomorphism field, think of a particle. I'll draw a picture here in a second to explain it. But traveling, it hits the diffeomorphism field, it stops basically. X of tau is basically the same. And then all of a sudden it accelerates like crazy to this next position, and then it stops. And as you can see, when n, which is the energy level of some sort of the Diffie field, um, when n increases, this effect increases drastically. Um, yeah, and this is a Minkowski space, flat space time. So in curved space time, I actually don't know what this would look like. We never got there. Here's some of the code for Mathematica. Um, we got the equations of motion here. Yeah. Um, yeah. These are some of our future goals that we sort of talked about. A few of these we got to in the spring. But yeah, some notices here that I'll. Anyways, um, here is the important part of. Well, why is my thing not working? Sorry, 1 second. What is this? There we go. Okay, does this work? Yeah, okay, okay. So basically, let's look at it this way. Can I scratch that out? Perfect. We have space. Okay, and then we have our particle. Particle. And the particle um the particle is gonna just travel in a straight line. Okay? And again, this is in flat space time, I'll say. Yeah. So this is particle where DAB is equal to 0. Okay. Well, uh, there's no acceleration. Well, maybe there is from like gravity and blah blah blah, but it's just going through space. Okay. Hmm. Oh darn it! Why did I do that? Here we go. Okay. I'm attempting to illustrate something here. Can I make this bigger? Perfect. Okay. Okay. This little yellow blob is going to represent um our DAB does not equal 0. So basically, here's what happens. The particle hits the field, the DAB field, the diffeomorphism field that arises from string theory, and it stops, basically. And then it accelerates, and then it stops, and then it continues on like nothing happened. So let's review this, if this makes sense. This is the big idea of the research. Um, and of course it's theoretical, so not necessarily, but mathematically it's valid. So we take a particle going through space, and there's no Diffie field, so it just continues going, no acceleration or anything. If there is a Diffie field where DAB does not equal 0, then it stops, basically. It slows down dramatically when it hits that field, and then in an instant, it accelerates in like a small, very, very small amount of time. It accelerates all the way across the field, and then it stops again, and then it moves normally. And that's the idea, basically, I think. I hope that makes sense. See if I can. Oh, it's horrible. Okay, bye bye. I hope this was a fun video to watch. Yeah. Bye.